My name is Yaron. I'm a developer on the JavaScript API, and with me
is Dario D'Amico, and I work with Yaron on the 2D WebGL rendering tier of the API.
We're part of the team who is building the rendering engine for the 2D API. We're also responsible for the vector tiles, and we also work with a team in Zurich on 3D. Today we're going to talk about building custom visualizations using WebGL in 2D map views. Then there's a question now, how we do this? We use custom layers and custom layer views. And then there's a question, why custom layers and custom layer views? So the answer for that is complicated, but kind of simple. Sometimes users need finer control over the implementation. Sometimes there is features that the out-of-the-box implementation does not support, and therefore there's a need for a custom layer. Some other cases, there's requirements to integrate with a data set that is not necessarily supported with the out-of-the-box API or services, integration with third-party rendering engines, and Dario is going to talk about this quite a bit later on during this presentation. There's sometimes specific performance requirements that, again, the out-of-the-box implementation may not be suitable for the needs of the client, and therefore there's a need for custom layer. And then there's a third question, which is why a layer and not something else, not like just a custom render or something like that. And then the reason of that is, from our perspective, is rather simple. A layer is a well-known paradigm in the world of GIS and visualization in general. Once something is implemented into a layer, from the API perspective, it is just yet another layer. You can reorder it, you can turn it on and off. If you're chosen to implement the hit test method, then pop-ups just show up with the data that you provide. And so basically anything that you can apply to a layer, you would be able to apply to the custom layer view, layer view that you would implement. Then another aspect is, why do we distinguish between layers and layer views? So this is something that goes, with the rest of the layers of the JavaScript API. We distinguish between layers, which are basically the data, and layer views, which are responsible for the visualization. The layer is responsible for loading, exporting, exchanging, querying, and so on of the data, whereas the layer view is totally responsible for rendering the data. When implementing a custom layer view and layer view, the developer must implement both of them. We provide a bunch of APIs to simplify the process and help the users to do the task. We'll go through some of the helper classes in details in the following minutes. And even more, if there are particular requirements or libraries that you guys feel that we need to integrate with, just let us know and we'll definitely consider that. Now, there's two ways to extend layers and layer views. As far as the layer, of course, layer is just a data, but then as far as the layer view, we let developers extend the layer views either using Canvas or WebGL. For Canvas, you can subclass base class base layer view 2D. For WebGL, you should be subclassing base layer view GL 2D. As the name implies, of course, refer to GL. And then as for when and how to choose between the two, and the answer for that is depending, of course, on multiple questions. What are the visual requirements? Is the data highly, is it static data or data that changes constantly? Is there a need to integrate with a third-party library that already using a particular rendering graphics API? What are the performance requirements from the custom layer and layer view? And of course, just as important, what is the expertise of the developer who is going about the task? Does he feel more comfortable writing WebGL code or simply Canvas, and so on and so forth? But we in any case, we let the developer choose the path of integration and extensibility, whether it's WebGL or Canvas. To start the demo, just give you some idea of what we're discussing. We'll show you two nice samples, one that I put together, the other one Dario did. This is a custom layer view that basically implement what looks like a feature layer with renders markers, nothing that you haven't seen before. You can change the color scheme. Basically, it's a unique value render, and by the way, it represents fuel stations. You can have a slider that changes the width, or consider it the width visual variable, as we refer to it in the API. But then on top of it, this checkbox simply enable a bloom effect that basically add a really nice post-processing effect to the rendering. You can change some parameters. You can change the intensity, the threshold, and so on. This is just a nice sample, and by the way, we'll try to make the samples available at some point, at least some of them. You can see, again, you can further change the color scheme. Just a really, really cool sample, and then I'm going to hand it over to Dario to show his demos. Oops. All right.
Hello. In this sample app, we implement the custom polygon layer to highlight the content of the layers underneath. In this case, the content is a Esri base map and a satellite base map, and you can click a country to enjoy fancy animation that is surely to draw the attention of the user to an area of interest, in this case, countries. This was implemented using custom layer views, frame buffer object, and the latest version of the ArcGIS API for JavaScript.
All right. So as for the implementation itself, so of course the base layer has to be subclassed, and then the user have a choice whether to simply implement everything as far as the visualization himself, or to let the API help by choosing to implement things through tiles. If tiles are required, all the user need to do is to specify the tile info property on the layer, and we'll see it in a second. Subclass the layer view GL2D. Of course, we're discussing about extending with WebGL, therefore it is this particular subclass. Implement methods attach, detach, render, and as an option, the user can choose or to implement or not implement the heat test. If tiles are involved, again, remind you that you need to implement the tile info property for that purpose. Then the user must also implement method tiles changed event for that purpose. When implementing the layer, of course, the way the API is built, once the view gets created, it asks the layer for the instances of the layer views. So when subclassing the layer, you also need to add the method that in 2D mode create the instance of the layer view. If, as mentioned before, if you choose to implement the custom layer view using tiles, then you need to specify the tile info. You need to create the tile info class that the API provides. This is basically defining the tiling scheme for the layer, where you can specify the tile size, the special reference, the level of details, and so on. Once you do that, as you zoom and pan, the layer would give you the information that you need for each tile, and of course that would be the row, column, level of detail. It'll be the extent of the tile, the bounds, the size, the width, and the height of each tile, and so on and so forth. And that can really make life simple. And then Dario would also show a sample of that soon. When implementing the layer view, of course, the user must override methods attach, detach, render, heat test. We're going to touch on each of those methods in a second. Method attach, as the name implies, is being called when they're being added to the view or when the view gets initialized. This is really where it is advised to initialize the different resources, particularly the WebGL resources. This is where textures should be created if they are static and don't change really. Buffers, of course, shader programs, and it's also the place to fetch resources that might take a while to fetch. Rendering context should and is being accessed through the this.context property on the layer view. The detach method, of course, it is the opposite of the attach, being called either when the layer is being removed from the map or when the map view is being shut down or disposed. Again, that's the place to do housekeeping and do the cleanup. This is the time to cancel, let's say, requests that are in flight and dispose any resources like textures, buffers, shaders, and anything else that is no longer needed and need to be discarded at that point. Just like the attach method, the rendering context is accessed via the this.context property. The render method, that's basically the heart of the implementation, is being called every time that the map view has to render itself. The signature of the render method accepts render parameters, which is object containing the rendering context, a Boolean indicating whether the map is stationary or not. This might be required for some developers, depending on the purpose and the implementation of the layer. And then the state object, which basically gives you the means to generate and compute the transformation for your visualization. This is where you can get the extent, the resolution, scale, rotation, the size of the window, and so on and so forth. And then on every frame, of course, you have to issue the rendering. We'll be touching upon this at the very end, but then, WebGL is a state machine, so make sure that you don't make assumptions on the state that you set on the previous frame. Make sure that you set everything that you need up front. The heat test, that is an optional method. The signature accepts an XY in screen coordinates. And then depending on your data structure, you define and figure out whether within, of course, a tolerance, under those XY coordinates, the user hit something or not. And if it did, then you return a graphic object with the information that you need. Could be the geometry, the point, could be some attributes. And that if you set the layer, as you can see here, the source layer, then the JavaScript API would also issue a pop-up with the information that you provide for that. We're going to show from here on. Dario is going to do a walkthrough explaining how to build a custom layer view. In this case, it's going to be the electric highways, and I hand over to Dario from here.
In this sample, we wanted to develop a custom visualization for a polyline layer, and we wanted to implement this electric effect. We implemented this using a custom layer view. So we subclass base layer view GL2D, and we subclass graphics layer to make use of its graphics collection. This is where the polyline features will be stored. And let's talk about polyline representation. So at first sight, these electric lines look rather complex, but as it's often the case in computer graphics, it's a trick. The geometry is quite simple. It's a very simple triangle meshes, and the electric effect is implemented using a fragment shader.
What is a triangle mesh, Dario?
Triangle mesh is a collection of vertices with some attributes connected together in order to form triangles. The triangle is the only primitive that WebGL can render efficiently and in a flexible way. So the idea is to basically map every vertex of the polyline into at least 2 GPU vertices, which will share the same position. This effectively means that the line in itself is a degenerate geometry because it has no width. But then each one of these GPU vertices will be associated to different offset vectors, which will be used by the vertex shader to extrude the polyline into something that actually has a width and can be rendered. Offsets are expressed in pixels, while geographical positions are expressed in map units. The vertex shader uses three matrices in order to implement the transformation and position the geometry on screen. The first one is the transform matrix, and is applied to transform coordinates from map units to pixels. Then there is the rotation matrix, which is applied to the offset vectors, and it works in pixel, in screen space. Then there is the display matrix, which is applied to the sum of the position and the rotated offset, and it converts from pixels to normalized device coordinates, which is what the vertex shader is supposed to output. This is how the three matrices are derived. The most complicated is the transform matrix on the left. It depends on several state variables. It depends on the pixel ratio, the size of the window, the center of the map view, its rotation, and also on the center of the map view the last time it became stationary. We will expand on these later. The other two matrices are much simpler. There is the rotation matrix, which is basically only takes into account the rotation of the map view. Then there is the display matrix, which depends on the pixel ratio and the size of the window. So in order to actually render something, we have to convert the polyline geometries into triangle meshes. And starting with version 4.14 of the ArcGIS API for JavaScript, there are methods on base layer WebGL 2D to do this. The method that we're going to use for this sample is Tessellate Polyline. It takes a polyline geometry in input, and it returns a promise that resolves to a mesh object that contains an array of vertices and an array of indices. It's a responsibility of the developer to map these vertices into GPU buffers using some sort of vertex format encoding.
What does Tessellate Polyline accept there?
So in this case, the polyline tessellation function accepts a geometry. And
what is this geometry? What type of geometry is it?
In this case, it's a polyline geometry.
And what is the 30?
30 is the width that the final line mesh should assume. It can be expressed in any unit that makes sense for the particular application. In this case, we assume that 30 is pixels. And these enable different geometries, different polyline geometries to have different widths. Can
I use a unit vector, let's say a size of 1, and then extrude it on the vertex shader myself?
It's actually could be a very, very common case, because yes, it's possible to use U1. This will mean that the polyline mesh has a width of 1, and then you can change the sides, the width, using the vertex shader and some information coming from somewhere else, probably a uniform. However, doing so would typically imply that all the polylines tessellated with 1 as a width parameter would have the same width. So in general, you may want to have polylines of different width, and so a width attribute is required. So that's why we actually provide the possibility of specifying the width here. So when Tessellate Polyline returns, you get a mesh object, and the vertices on this mesh object have several attributes. The 4 that are relevant for this sample are position, then there is the offset vector, then the distance from the start of the polyline, and then a pair of texture coordinates, for a total of 7 values. It's a responsibility of the developer to copy these values on the GPU. In this case, we opted for a simple vertex format in which we use float for everything. So you can see that position x, y, offset x, y, texture coordinates, and distance are mapped into 7 float values. And then we also come up with 5 additional attributes. One is the total length of the polyline. We want every fragment to have access to the total length of the polyline in order to implement some advanced animation effects. And also we encode 4 random, pseudo-random seed values, which again will be used in the vertex shader to introduce some variation between polylines and make the visualization look more interesting.
You say that the position is given in floats. Is it going to hold the geographical vertices? Nice.
Yes, actually we don't actually encode the position in the global position in, let's say, Web Mercator coordinates, because these are actually very, very big numbers. So usually the coordinates that we have in GIS are too big to be manipulated correctly and precisely on the GPU. And this is actually what happens if we use global Web Mercator coordinates. You will see that as you pan and zoom the map, the line, the polyline wiggles and snaps and behaves in some sort of weird way. So what we actually do to combat this problem is we adopt a local origin. Every time that the view becomes stationary, we consider the center, we assume the center of the view as the new local origin, and we encode attributes which are relative to that local origin. This keeps the numbers smaller. Obviously, since we are effectively encoding a different attribute which is partially transformed, we also need to we also have to modify the transformation matrices in a way that is respectful of this change. And in the end, we end up with values both in the attributes and in the uniform, which are smaller and easier, and that can be handled in a more precise way by the vertex shader. And as you can see, the line doesn't wiggle anymore, and everything is smoother. If you want more information about local origins and the floating point precision issue, check out this SDK sample where we discuss the problem at length.
I'll also talk about this at the very end of this session.
So when do we actually need to write to the vertex buffers? There are 2 conditions. The first one is obviously when the layer.graphics change. Every time that there is an addition, a removal, or some sort of change to the graphics collection, we need to regenerate the geometry that represents those graphics. So we listen for changes to the layer.graphics collection, and we schedule, if needed, an update on the next render cycle. But there is another condition that we have to take into account. Every time that the view becomes stationary again after having been moved, like after the user pans or zooms, we actually need to re-encode all the attributes all the attributes again in order to adopt a new local origin for the position attribute. We made it to fragment shading. So this is the process that will actually assign a color to the fragments. Fragment shading conceptually happens in 2 steps. Step 1 is getting the intensity value. So basically we associate a monochromatic float value to each fragment, which in a way represents the amount of electricity in the fragment. Then we shade it, so we make it blue using a separate shade function. And we actually compute 4 different intensities for each fragment using 4 different random seeds. And these will be responsible for each polyline carrying 4 separate and different electric beams. So the first contribution to the intensity of a polyline is given by a faint low-intensity glow that is shaped using an inverse parabolic function. This function is responsible for an intensity field which is maximum at the center of a mesh, and it's fainter at the edges, so at the beginning and at the end of the polyline, as well as close to the left and right bank of the polyline. In addition to this, we use a sine function, a time-dependent sine function, to trace a high-intensity beam. And we also use a sine function to make the brightness, the intensity pulse over time, and again make things more lively and interesting. Finally, we compute a spread factor, which makes the sine function less large at the beginning and the end of the polyline, and this is responsible for creating this effect that suggests that the electric beams are originating from a point-like source and are ending into a point-like sink. Now it's the time to shade this intensity. The first step is choosing a color. In this case, we choose an electric bluish color, and we use the intensity value up to the first unit. So we clamp to 1 to decide the brightness of an emissive blue material. And also we use the intensity in excess of 1 to drive an additional emissive material, which is white, and this is responsible for the bright core in the middle, in the center line of each electric beam. And as we mentioned before, we repeat the intensity simulation 4 times with 4 different random seeds, so that we end up with each polyline carrying 4 distinct electric beams. We made it to the rendering method. So the render method of the base layer WebGL 2D is responsible for binding the electric effect program, update the uniforms, bind the buffers, enable and set up the attributes, enable premultiplied alpha and other WebGL states, like for instance we disable face cooling, and then finally we can draw all the polylines using a single call to draw elements. For more info, please check out the sample. It's going to be on CodePen as all the other samples from now on. And now back to you, Yaron.
Okay, so many times when implementing a custom layer, it's more than just rendering markers, even though, and as you know, GIS features cannot be just directly rendered with WebGL. We have to go through a process of triangulation or tessellation, which means take the underlying geometry and break it into triangles that WebGL understand. This is quite involved in terms of the computation, and it's there's quite a bit that is required to do. So we provide some helper functions, to do that. There is a tessellate polyline, which takes a polyline to generate and then returns a mesh, a polygon, extend point, and a multi-point. Have a look at the tessellation helper, and then there's an SDK sample, excellent sample that Dario put in place. Dario, can you please show that?
So this is a sample that shows how to use all the tessellation functions, not just tessellate polyline, to create triangle meshes for different kinds of geometries. We have a polygon with a hole, we have point geometries, multi-point geometries, we have polylines, and we have an extent. And notice that we tessellate the point and multi-point in several different ways, because we have markers which are screen aligned and markers which are map aligned. All of this is made possible by the new tessellation functions. In this sample, we discuss how to use all of 5 of them. And not only that, we also discuss how to implement a unified vertex shader and fragment shader that is enabled to render all different geometry types.
So this example, this walkthrough and example are all available in our API?
Yes, they are. We actually invite you to check them out. This sample is very interesting because we show how to build a texture space on each one of these geometries. You can see it because the lower left corner is black and the upper left corner is yellow. So this means that you could map a texture on top of these features. And we invite you to play with this sample. You could, for instance, change the color. If you actually want them to look solid red, you could do it. And so you can experiment with them and come up with interesting visualizations.
This is very cool.
Thank you, Yaron. Back to you.
I'll talk about it and you continue. So accessing the back buffer. Many times when implementing custom layer visualization, you may need to access the WebGL back buffer, whether because you need to read the bits from it so that you later on blend against it, or for any other purpose. Maybe you need to use your own off-screen frame buffer object to do your own processing, and eventually you want to rebind the current back buffer. To remind you, WebGL is a state machine. For that purpose, there are added a bunch of utility methods on the base layer view. One of them is the get render target, and the other one is the bind render target. Maybe you can go through that.
Yes, these new features are used in this sample app. It's a bevel feature visualization. So basically we start with a base map, and on top of this we render a custom layer view, which is actually a thematic visualization in which the population drives a color visual variable. So where you see a more saturated red color, it means that the population is higher. And to this thematic visualization, we apply a multi-step rendering, a multi-pass rendering algorithm. And the first step is to turn this into a normal map by computing screen space derivatives. Then we blur this normal map to reduce noise and make the edges appear smoother. We use frame buffer objects to store the intermediate results of the computation. And the final step is to simulate a light source shining from the upper right corner of the screen on the normal map, and the results of the lighting model is applied to the original thematic visualization, which in many ways counts as a diffuse color map. And so basically with this app we implemented a normal mapping entirely on the fly, starting from a thematic visualization.
Very cool.
Thank you. And now Yaron is going to talk about tiling.
Okay. So as mentioned before, many times, either because of your data or because other considerations, you want to render your data in tiles. And in order to get the tiling scheme, all you need to do is add property tile info onto the custom layer that you subclass. You use our own tile info object to instantiate the scheme. You can specify the tile size, the original special reference that your data is in, the number level details, and so on and so forth. If and when you do that, we would give you a list of tiles that you can access through the this.tiles property on the layer view. And you also, of course, remember to need to implement the tiles change event handler, where we would also give you the list of tiles that have been added and the tiles that have been removed when the transformation changed. Then on your end, you can use those tiles, you can add additional data to those tiles, or you can use in a containment model to contain them in your own tile object. And then during the render loop, all you need to do is iterate through the tiles list and then render each of those tiles by yourself. Dario is going to show a sample that is part of the SDK that shows how to subclass a custom layer view using tiles and render those in tiles.
So in this sample, we have a base map, a satellite base map, and on top of this base map, we render a custom layer view, which displays mostly semi-transparent tiles.
So the network is kind of slow for some reason.
Taking a while to load.
Hopefully the network is on. Maybe try refreshing the display.
Yes.
All right, there you go.
So on top of this base map, we draw a custom tiled layer view, which is mostly transparent, but each tile has a white border and a white tile ID in the upper left corner of the screen. So in this sample, we use the base layer view gl.tiles property, which Yaron talked about, to decide what to render. So this is where, for instance, we get the tile ID from, and we use this information to draw something on the textures of the tiles. And it's very easy to actually modify the code, for instance, to render a double border. We can do something like this, and we will end up with each tile having a double border. And not only we get the information about what to render, but we use the tiles collection to also decide where to render things. If we take a look at the render method of base layer view, we see that for each tile, we actually take the information of its coordinates and of its sides to derive a rect, xy width height rect that we pass as a uniform to the vertex program, so that the vertex program will be able to position this tile in the right place, in the right part of the screen with the right rotation and everything. We encourage you to check out the sample. It's very easy to modify to display something else, and you could even modify to load the custom images from your own tile server.
Okay, integration with third-party libraries, that's a big thing, and this is part of the theme of this talk. We understand that there's a bunch of visualization libraries, such as some of them are also geographical, and we try to make it simple and easy to integrate the JavaScript API against those third-party libraries. They're in the next series of slides that are going to talk about the integration with some of those. And we work closely with deck.gl, which is given by Uber, on allowing an integration point, our API, their library into our API and vice versa. You can find the samples on both ends, and Dario is now going to do a walkthrough on implement integration with deck.gl.
So together with the visualization team at Uber, we developed an NPM package. It's called deck.gl ArcGIS. You can get it from unpackage.com and use it to build a custom layer view based on deck.gl. The way you do it, you can import the main deck.gl module from Unpackage, then you import the deck.gl ArcGIS extension, and then you import the ArcGIS API as usual. So you use the require function to load the ArcGIS modules as usual, while the deck.gl distribution will be available on a global deck object. This deck object has a method called load ArcGIS modules. You can call it, and this method returns a function that resolves to an ArcGIS object. This ArcGIS object has a class, deck layer, which we developed jointly with Uber. And this is basically a custom layer view. It's derived from base layer view GL2D exactly in the same way that you have seen during this whole presentation. And it basically acts as a container of deck.gl layers, and then you can add it to a map view as usual because it's a layer. So this is cool because it allows you to bring any deck.gl layer stack into the map view and display it on top of Esri layers and Esri base maps. We have an SDK sample for this. It shows you how to import the deck.gl trips layer, which is an additional layer type. It comes from a separate module, the geolayers module. This is a work in progress. It will be ready by the time 4.15 is released. The API is still a work in progress. The deck.gl extension API, the ArcGIS deck.gl extension API is still a work in progress, but it will be finalized in the coming days. So be sure to
4.15.
4.15.
Right.
So be sure to check this sample when 4.15 is released.
Can you hook that trip layer with a different data?
Yes, this is actually one of the main motivation that you could use custom layers for. If we open the code, you will actually see that the data is coming from a JSON file that could be a custom format file, and you can replace these with something else, and the visualization will depict the data, take the data from there. It could be your arbitrary format, it could come from some sort of WebSocket dynamic page. It's up to you. The possibilities are endless, really.
Okay, in addition to integrating with deck.gl, Dario also provided integration with luma.gi, which is a lower level library that renders with WebGL. It is very similar to raw WebGL, but it's It makes life much easier than writing WebGL. Dario will talk about the details here in this slide, and the rest of the slide, and the demo that he's going to show.
So lumagl ships on a CDN on unpackage.com as part of the deck.gl API. So you can import the deck.gl main module, and the Luma toolkit will be available on the global Luma object. And then you can also import the JS API as usual, and you can start building custom layer views using luma.gl. The first thing that you probably will want to do is in the attach method of your custom layer view, you will want to call luma.instrument.gl-context.gl. This polyfills the GL context of the map view in order that it can be used to Luma methods and classes. In Luma, there is the concept of geometry, which is basically an object that brings together index data, vertex data, and the description of the attributes that are found in the vertex buffer. And then you can bind the geometry together with shading information, including a vertex shader, a fragment shader, and a specification of uniform values, and this is called a model. A model is something that has all the information needed for rendering. One of the nice things about lumagl is that it abstracts away some of the WebGL details, in particular the global nature of the WebGL state, and it makes writing code easier and less error prone. In this snippet, we call luma with parameters method in order to set up the WebGL state to something that will make this model render properly. And after the callback returns, the WebGL state will be reverted to the original state, and this makes writing code much easier. In this case, the model is rendered by calling the draw function, but before calling draw, we also set the uniforms to something that will position the model properly and configure the shading system in the right way. We have a sample for this. It's available on CodePen. It's an updated version of an older WebGL sample, the first WebGL custom layer view sample that we had. It's the pulsing marker sample. In this case, we updated it to use lumagl, and we made the visuals fancier. We encourage you to check it out on CodePen. For instance, what you could do is change the color of the markers. You can also change the number of rings and play with it and come up with different visualization and modify so that it suits your needs and can provide a starting point for your own custom layer view using lumagl. And in addition to this, we also worked with Three.js. Three.js is a high-level 3D WebGL rendering engine. It's much more high-level than Luma. It dramatically reduces the amount of lines of code needed. In order to use Three.js, you import the main Three.js module together with any additional module that you may want to use, for instance, in this case, the GLTF loader. And once you've done this, all the Three.js core classes like scene and perspective camera, but also any additional class like GLTF loader will be available on a global Three.js object. So when you are using two different rendering engines together, usually some work is needed in order to make them play nice with each other. In the case of Map View and Three.js, we need to do two things. One, we need to tell Three.js to not erase the base map, basically, because the default behavior is for Three.js to clear the color buffer at every frame. We don't want this to happen. And the other thing is that since Map View resets the WebGL state every time that control is handed to a custom layer view, we need to tell Three.js about this, because otherwise Three.js would assume that the WebGL state is the same at the beginning of a render cycle as it was the last time that a scene was rendered.
Remember that WebGL is a state machine, and since both libraries share the same rendering context, we cannot assume that the state is the same. So we have to make sure that we reset the state every time we switch between one library to the next one when we render.
Exactly. The other thing that typically you would want to do, in this case it's because we are using a 3D API together with a 2D API, is to match the 3D camera with the 2D viewpoint, so that the 3D objects in the scene appear to be anchored to the base map in the right way. The way we suggest to do this is to use a perspective camera and to set the far plane of the camera in a way such that the back face of the viewing frustum matches the viewing extent. Once you have done this, you can place your 3D objects on the far plane with their base on the far plane sticking out towards the screen, toward the camera. And the way to do this is to use the 3.js unproject function. You can pass a point where the x and y coordinates are the x and y screen position of the 3D object where you want it to appear, and then you supply 1 as the third coordinate. 1 represents the back face of the clip cube, of the clip volume, and when you unproject something on the back face of the clip volume, you obtain something that is on the back face of the viewing frustum, which is exactly what we wanted in this case. Something else that you could do with 3.js is use it to implement the heat test function of your custom layer view. You can use the 3raycaster class, and you have to be careful here because very often 3D objects are multi-part and they are hierarchical. So when you actually raycast against a scene, you usually want the raycasting to be recursive so that it hits potentially a child object, but this also implies that you don't know exactly which object will be returned. It could be the main object, it could be a group object, it could be one of the children parts. And so usually your heat test method must be smart enough to understand how to create or look up the correct graphics that must be returned to the user, because ultimately heat test must return a graphic. We have a demo that showcases this. This is a custom layer view on top of a base map. In this case, we are centered on Central Park in New York City. We have a landscaping widget, we can call it like that, on the upper right corner of the screen, where we can select different kinds of trees and place them on the scene. We have different kinds of trees, we have houses, we can place houses and even giant ducks. So all these objects are rendered using 3.js, and as you can see, the perspective camera is creating the perspective effect, but they are still correctly anchored to the base map. Also note that this layer view supports heat testing in the way that you expect it to work, including the default pop-up behavior.
Very cool.
Thank you. Now back to you, Jeroen.
All right. So that brings us to the last part of this talk about some WebGL gotchas. I mean, after all, this is a presentation about implementing custom layer views with WebGL. So as Dario showed just before with the electric lines custom layer view, precision is an issue with WebGL. Well, WebGL can only handle 32-bit floating point and that is somewhat trouble when it comes to using geographical data. If you look at WebMercator, there is a coordinate span of 40 million meters. Whereas if you look at the standard for a 32-bit floating point, the number part can only handle 23 bits, which is effectively giving us about 8,400,000 units. So as you zoom in, and always rendering is involved in some use of some form of a transformation matrix. There is also a translation, need to bring the object from far away onto the view. The precision of the translation would simply not be enough, and then the object would eventually start wiggling. Of course, in order to mitigate that, we use local regions, we're using tiles. There's a bunch of other options in the talk that I gave with Jan. We also discussed that. Can please go? So here's a sample that I built to demonstrate the problem. This is a custom layer view that render marker layers. It is doing a pretty trivial transformation. As I zoom in, you see that the markers start to wiggle. And of course, this is really not acceptable. You know, nobody likes to have data that wiggles. The solution for that problem, in our case, is to use tile. So there's another sample. In this case, I'm simply organizing the data in tiles. And the idea is that each tile has effectively its own local region. So when rendering, I'm simply, before rendering, computing the transformation matrix for each tile and then render it. And then the geometries within the tile render relative to the local region of the tile, and therefore they simply don't wiggle. I can zoom in as much as I want, and the geometries would be fixed and anchored to the geographical location, and you can see I can do it all day long, and they're not going to budge. Going back to the slide. Another problem with WebGL to bear in mind, again, is WebGL is a big, giant state machine. So then when you're implementing your custom layer, whether you're writing pure WebGL or using a third-party library, whether it's Three.js or deck.gl or any other library, make sure that we need to understand that the state cannot be guaranteed to be the same in between draw calls. What I really mean by that is that when you render, you're setting your own state, you know, whether you're binding textures and setting blend modes and shader programs and whatnot. Once the draw method is issued and called again, you cannot assume that those resources are still bound to the context, because in between the previous call and the next call, the API rendered and is resetting the state, because on our side, we're also keeping track of the WebGL state, and we have our own internal abstraction. And because of that, we need to make sure that we don't mix with the state that the third-party libraries are setting. So we must reset that state before carrying on. So that, bear that in mind. And again, it's always good practice to make sure that you set the state before you render, regardless of, by the way, whether or not you're integrating with us or any other third-party library. Another thing to bear in mind is that calling WebGL can really only be done under the proper call to request animation frame. This is really where the map and map view renders. So the method detach, detach, and render are guaranteed to be called under request animation frame. Calling WebGL outside request animation frame can either result in really bad performance or even a crash in a worst case scenario. So if you make an asynchronous JavaScript call to either fetch resource or do anything like that, make sure that you don't necessarily dispatch WebGL instructions at the end of the callback. Make sure to, if you need to, delay that and only make the call during the next render, the call to render, or again, attach and detach and so on. So, by the way, speaking about performance, WebGL doesn't also like state changes. So in that case, you need to make sure that if you can batch data together, it's always a good idea to reduce the number of draw calls, or even more, the number of JavaScript instructions that you generate. That is basically concluding our talk for now. I think we covered quite a bit of ground. Thank you. All the SDK samples are linked here, and Dario was gracious enough to put his samples in the CodePen samples. Dario?
Yeah, so they will be they're available as a CodePen collection. You can click here, and sometimes PowerPoint doesn't like it. But basically all the samples that we dissected so far, like the electric highway, the bevel features, the deck.gl, the luma.gi sample, and the Three.js sample are available as a collection. Thank you.
Thank you so much.